Okay, so the plan for today is to go through one of the Kalman filter problems and to solve them by hand. And probably by the middle of that lecture, you will understand why I hesitated even to start doing that. Hopefully, I will not do too many mistakes, but I will publish the entire solution online, so you'll have the actual printed version of that entire thing. We will go through the formulas and we will try to implement that for one-dimensional system, one-by-one system, which is unheard of in this course, right? But we will do some simple problem. So you have, for example, zero location for a ball, it's falling down. We get the location of the ball sampled at particular points. Okay. Obviously, you have gravitation force, right? And this gravitation means that you have constant acceleration free fall. So releasing the ball here, it starts to fall to the ground faster and faster and faster and faster, right? Now, the point is to estimate the gravitation constant, which means g. Okay, so you have acceleration equals g. Typically, it's 9.81, something of that kind. But let's say we don't know that. Actually, I've heard that some textbooks here are even using 10, which is whatever. People like round numbers. Let's also to 9.8. So we want to estimate that constant. Okay, and this will be extremely simple model. What kind of model is that? If this is your state, so x equals to g, one-dimensional system. And you also know probably kinematics formula, which would say that output of that system, which is the measured output, will be gt squared divided by 2. It's a straightforward equation. You remember something from mechanics, physics, kinematics, whatever. Right? So this is the output that you are measuring. So you're measuring at these points, equal time intervals. So you get y0, y1, y2, and so on. And this is what you expect to have, but let's say you do not know that thing. You do not know that constant. You want to estimate it from your measurements. You want to measure g actually, given your y. Okay? This is the problem that we are trying to solve. So what would be our state space model for that? So our state space model is standard thing. In that case, we don't use dot, we're using k+1 because we need Kalman filter for discrete states. A xk plus b uk plus g omega and y k equals c xk plus, let's ignore the d part, plus vk. So it's okay. Now pay attention that each one of them also could be a function of k. Because Kalman works fine with time variant systems as well. So each of the matrices might change in time as well, if you want to. All right. So what is the type of models that we are using here? So we are estimating g, constant of gravitation. The key word for your answer is constant. We talked about that last time. What kind of model is that? Okay. We need to write that thing. X k plus 1 equals. First of all, let's start with something simpler. Okay. What are the dimensions of matrix A? 1 by 1, it's scalar. It's just constant number. Okay. What is a number which multiplies xk? If you're assuming that we are estimating constant of gravitation. You want to multiply each next by 9 by almost 10. So you're saying that every single time your G will become 10 times bigger, every single time you measure it. So what is a constant? Will it change?
So 1.
1. This is your A matrix. Next state equals to previous state. Constant position model. So in that case, it's not constant position, it's constant acceleration. This is what we are estimating. So for us, it's constant variable. Variable is not changing. Our assumption is that this thing is not changing, potentially up to noise. But let's even ignore the noise. We will say, well, gravitation is not really changing, right? So there is no noise in gravitation. It's not like one time it's 9.81 and other time it's 82 or whatever. Okay, so it's always constant. There is no measurement noise, and not measurement, model noise. So this is like entire thing. This is a full equation that we are solving, okay? As simple as it could get. So this thing will be 0. This is our assumption. All right, and this is our model for that equation. We also do not have any input to it, right? So there is no input, which means that this thing is also 0. So we do not have any inputs to gravitation. Gravitation is constant. And this is how you describe that gravitation. Now, it depends on initial conditions. Okay, if you start with 0, it will be always 0. If you start with 10, it will always be 10, right? So it's not changing anything if you're using only that model. Right, so this model will be pretty horrible if you're starting with wrong initial conditions. If you start with 9.81, it will be perfect. You don't need any measurements. You got it right. But the point is that in reality, you don't know that number, right? You want to estimate it. So you'll start from somewhere else, and you'll start with some other x0 estimated, right? Not 9.81. And then it will need to converge somehow. So what are the y equations that we have here? So what is yk? What multiplies xk?
Same 1.
Hmm?
1. It is not.
So yk equals xk, which is g. Y equals g. Y not equal to g. Y equals, let's say, different points k. So this will be particular time at index k. This will be particular measurement at that particular index k. So what is that thing here? What is our C matrix? So this is obviously A matrix, right? It is A, B equals 0, A equals 1, C equals something, B equals 0, so on. So what is that C? You have formulas there. Just read the formula. Use your CK in that case. This is what it is based on the formula. Okay, so this is what you actually measure. All right, and then you have some additional noise. VK. Measurement noise. So your measurements will not be exact, precise. Your sensor will be a little bit wrong. And this is how you define it. It will have zero mean noise plus some standard deviation, whatever the standard deviation is. We'll call it sigma a squared or whatever variance of that noise. All right. So here are the things that we have here. Okay, I will just summarize what is given in our problem, right? All of the variables. We'll have some reference. So AK will be always 1. BK will be always 0. CK will be 1/2 TK squared. GK will be 0. And then you have WK equals 0 because you do not have any systems noise. VK equals some constant. And this constant also can change in time, so it doesn't matter. Your variance could be constant or changing in time, doesn't matter something. Okay? Any questions so far? Okay, now we can do the actual computation of Kalman filter based on all these variables. Right, so now let's move to another board. Okay. Let's start with the initialization of the system. So we start in the system with particular x0 estimated. This is before the measurement, which is minus. We can choose that practically is anything you want, any number you like. You can start with 0, for example. You can start with 10, you can start with 9.8, you can start with whatever you want, if you don't know anything about machine, right? So let's start with 0, it will be simple, okay? Some stuff will cancel out if you start with 0. But you can start with something closer to the actual gravitation constant, and then it will just converge faster. This is the only difference that you will have, okay? So if you start with something which is closer to the real state, it will converge to the true state faster. But we will start with 0, okay? And we will do a few steps, a few iterations to see where we get with it, with all these formulas, okay? Now we can also choose P0, which is covariance matrix. In that case, what dimensions we need to have to that matrix? What are the dimensions of P? P is the covariance of state, which is E of the arrow.
Should be A, the same size as A.
Same size as A, yeah. So it's scalar. So let's call it P0, small P0, okay? Some number. Should that number be big or small? And how do you know? What does it mean, that number? Like, what is the meaning of that number that you choose? It's uncertainty about your initial error. Which means if you are pretty close and you're pretty sure that you're close, like if you choose 9.8, this number will be relatively small. But if you do not know anything about your estimated state, then this number should go almost to infinity. It should be a big number, huge number, because you want that Gaussian to be very broad, okay, to include all kinds of possibilities, which means you're saying, well, my initial position is somewhere here, okay, from there to here, okay, not here, but broad. This is the overall idea. So larger that number is, more uncertainty you have about where your initial position is, practically speaking, okay? In that case, you will choose some number P0, so we'll go with the number P0, but you can substitute any constant number here, okay, whatever your knowledge about your system is, right? Okay, so this initialization, you have all these two numbers, and we will start. Yes.
So you said the number, it can be anything. So can I consider
Typically,
it?
it's like big number, close to infinity, 1 million.
So instead of considering a really huge number, can we say something like plus or minus 9.81 so that like you have a certain range to cover instead of considering like Gaussian curve like till infinity. We can restrict it.
If you start, for example, with zero and you know physics, obviously you will not choose at infinity, right? So you know it cannot be like more than 20, for example, or less than zero, because it has to be positive, right? So you know that your standard deviation should be covering number close to 10, starting with zero. So you can choose that number, okay? And I mean, you can choose even number of 9.8 and then standard deviation of less than one. That's okay, right? Because you know it will fit in there somehow. But again, we are trying to broaden the scope here, okay? Assuming that we don't know what G is. We have no idea what G is. We just want to find it somehow from measurements. All right, this is the idea. Okay, so this is first step, and then we have measurement update at the stage 0. So we'll do measurement update for k equals to 0. I'm just copying the formula for k0 from the Kalman filter. The formula looks like that. I'm using like instead of k coefficient, I'm already substituting k equals to 0 here for all the indices, okay? So it's p0 minus c0 transpose times in parentheses c0 p0 minus c0 transpose plus v all that inverse. This is the formula for K, okay, Kalman game. Now pay attention that all of the things are scalars, right? Just numbers, so you actually can divide this one by this one. You can write it in more compact form, like a fraction. This is only for one-dimensional systems. Like, don't repeat it at home for any other systems. But this is how it will look like. It will be P0 minus C0 transpose divided by that thing. I'm just copying that same thing. Okay. Now I want to get rid of that part to simplify that algebraically a little bit. Since I can, because I want to get to the formula which will make some meaning to us later. Okay. I'm dividing numerator and denominator by P0, C0 transpose. Because you have same thing in the numerator and denominator. So at the top you will have 1. And at the bottom I will have C0 plus V divided by that C0, P0 minus. Something like that.
And C0
C0 transpose. Right? 0. In that case, it doesn't matter in which order it goes. It's 0 here plus v divided by that thing. Change the order so that it will be consistent. So now I'm substituting C0 and all these numbers, and you will get twice T0 squared P0 divided by T0 to the power 4 P0 plus 4 V. Something like that. That gets to algebra now. In our case, T0 equals to 0. You just start with 0 time. So it will be 0. Okay. Next thing we need to estimate is x estimated 0 plus after the measurement update. Now you have y0 coming in and equals the full formula will be x0 minus estimated plus k0 times something. Y0 minus C0, x0 minus estimated. That will be 0 because we started with x0, right? Plus again 0, which is zk, which we computed here, times y0 minus t0 squared divided by 2 times 0, which obviously will be 0. It looks like we will never get out of that 0 somehow. That's okay. First step, everything is 0. And the last thing that we are doing in measurement update is p plus 0, which the formula for that is p0 minus k0 times c0 times p0 minus, that will be p0 minus 0, which is p0, so it hasn't changed. Measurement hasn't changed our estimation of covariance. It's still the same initial p0, right? So this is measurement update. Now we have time update. For k equals 0, which means we are trying to predict the k plus 1 step. What will happen to the k plus 1 next step without having any next measurement, which is t1 measurement, right? Okay, so let's see what we get. Here are the formulas. x1 minus, which is at k plus 1, and k is 0, so k plus 1 will be 1, equals a times previously estimated x0 plus bu0, and obviously it will be just the previously estimated k0 plus. And again, we get 0. Nothing interesting is happening so far. This Kalman filter. You don't need that complicated formulas to estimate zeros. But that's okay, we'll get that. P1 minus will equal A times I minus K0, C0 times P0 minus H transpose plus GWG transpose. This is a formula. It will be 1 minus 0 times P0. And again, nothing interesting. Still P0. This was the first step. Like one iteration in Kalman filter. These are the formulas. Okay. Now we're going to the second step. One. Repeating exactly the same formulas, same thing. K1. And I'm jumping already to that thing. just replacing everywhere zeros with ones, right? Should the same formula. That will be 1 C1 plus V divided by P1 minus C1. And the result will be 2T1 squared P0 divided by T1, the fourth power P0 plus 4V. Similar to what we got before, just with index 1. Same thing to here, just placing with 1, same formula. Okay. X1 plus will be K1 Y1 minus 0. So in that case, Y1 will not be 0 anymore, right? Because it's already falling down. So your second measurement will not be around 0. It will be somewhere wherever it measures, wherever your sensor says. Okay? It could be noisy measurement, but you still have some measurement. You cannot have that 0. So now I'm taking this thing and multiplying by Y1, right? Because this is what it is. So you get same formula, 2T1 squared P0 Y1 divided by T1 for 4 P0 plus 4V. So this is our new estimated X1 after the measurement Y1. Okay. Now P1 plus will be P0 minus K1 times T1 squared divided by 2 P0. That will be P0 times 1 minus T1 force P0 something like that. So I'm taking like P0 out of the parentheses here. So here you have 1 minus K1, which is that thing times T1 squared. So T1 squared multiplied by T1 squared will be T1 fourth power, and so on. You get that kind of stuff. Okay. And last thing is time update. For time update, you have x2 estimated minus equals ax estimated plus 1 plus b u1, but this part is 0, so you don't need anything related to bu, and you will get twice t1 squared p0 y1 t1 to the fourth power p0 plus 4d. So this is your next estimated state, which seems to be pretty complicated, but this is what it is given generic p-value, okay? And p2 minus will be same formula. So get exactly the same thing. This one. Then you continue for k equals 2, 3, 4, 5, 6, 7, whatever. Right? So we did practically 2 iterations. And it's already pretty complicated. And for one-dimensional system. So you can imagine how it would look like for 2-dimensional system or 3-dimensional system. You're doing more iterations. For computers, it's a piece of cake. You just write in the formulas, right? Multiplying matrices, inverting matrices. It's okay. But what I want you to put attention to get some attention to the final results here. Specifically looking on the estimated values, which are this thing, and maybe this thing, which is kind of close. We can talk about that thing. Maybe also about C. Okay, let's talk about that thing. So obviously that x2 is your estimate for your g after the second step, right? So what would happen if you do not have any noise, which means v, which we call also sigma squared. So this is consistent here, this is v. So v is sigma squared. This is the variance of noise. So what happens if v equals to 0? What do you get here? Can you compute what happens if v equals to 0? What would be your estimate for g? So if v equals to 0, then you have this thing divided by this thing. So t1 squared canceled with 4, so you get like t squared here. P0 canceled with this one, but it will be twice, like 2 divided by t squared p. No, p is canceled. It will be 2y1 divided by t squared. So what is that? It's exactly the formula that you have there. Why is that? Does it make sense if you will get that type of estimate? What does it mean that v equals to 0? Like what is the meaning of having variance of your sensor 0? I'm sorry. What kind of sensor is that? It's perfect sensor. It's ideal sensor. Your sensor measures exactly the distance, okay? The distance is super precise, which means that you believe your sensor infinitely, okay? Whatever it measures is complete truth. So you don't need even any model, right? You can just trust your sensor completely because your noise is completely 0 here. You trust your sensor, whatever sensor says, and you know formula for the dynamic model, right? So just put that y number in the formula and compute it back, your g. So it's like from the original formula that you have there, which is y equals gt squared divided by 2. You just compute g. G is equals twice y divided by t squared. That's it. And since you know exactly the y, and you know that this is constant number, you know exactly the t. That's it. You don't need anything else to compute g. You just actually compute g, not estimate g. You compute it, right, from the values that you have. Why? Because your noise is 0. But let's say your noise is not 0. Okay, so v has some positive values. It's some variance of the noise. What will happen if your uncertainty about your p is infinite, which means p0 goes to infinity? What would be that limit of that x2 when p0 goes to infinity? Like you want limit of that thing when p0 goes to infinity. What is that? How do you compute that? Do you remember how to compute limits in calculus? Technically speaking, this is exactly the same thing as you had before. Why? Because this one is something huge, and this one is tiny compared to that huge. So this thing, this could be ignored compared to this part. So you'll have this part ignored compared to this part, so you'll have this one divided by this one, which gives you obviously the same answer like here. Why does it make sense? But if P0 goes to infinity, which means you have huge uncertainty about your initial state. Your best estimate is what to do, initially at least. To believe your measurements, you have no idea where it is based on the model, okay? You start from completely random point. You can start with 1 million, whatever. But your measurement says, no, it's 10, okay? Whom should you believe? 1 million or 10? Sensor. Of course, your sensor, you believe more your sensor, so you trust your sensor almost completely, okay? Because you have no choice really, because you have complete uncertainty about where it was from the beginning. Okay, it started somewhere at a random point. Okay, it could be super far away from your true value, or it could be close. You don't know. You have nothing. You have no idea where it is. So your best instinct should be like try to believe your sensor, because this is what you have already. You measured something and it says it's 10. Okay, so believe it's a 10. Just use a 10, whatever it is. Okay, with time you will get more and more data, so you will get closer and closer, right? But at that point, you have no idea if P goes to infinity, okay? You just started somewhere at random point, and then you converge to something, right? Any questions?